Some places in space are almost perfectly silent to our instruments. They register almost no particles and barely any radiation. This video points out the quietest spots astronomers have measured. Immediate result is simple. Extreme emptiness causes very low noise. I will show examples and measurements and explain why silence matters. So expect regions with vanishing gas and only faint signals. A vast emptiness stretches between galaxy clusters, like a dark ocean. Astronomers call these regions intergalactic voids, extremely low-density spaces. They matter because they set the quietest electromagnetic baselines we can measure. Gravity still sculpts voids, but far less matter sits inside them than elsewhere. Few atoms means almost no collisions, and therefore much less thermal radiation. Magnetic fields there are weak, and radio emission drops dramatically. The Boots void spans about 300 million light-years across and hosts far fewer galaxies than expected. Telescopes counting galaxies find only a tiny fraction inside that volume compared to average space. So voids act like the calmest cosmic neighborhoods we know. Our sun sits inside a roomy cavity called the local bubble. The local bubble is a low-density region carved by ancient supernovae. It matters because lower particle density reduces background noise for many observations. Blast waves pushed gas outward, leaving a hot but rarefied interior behind. That thin gas has far fewer neutral atoms, and so less radio absorption occurs. Magnetic structures are stretched, and cosmic ray paths change inside the bubble. Measurements show densities as low as about 1/10 typical galactic values by number. These conditions create quieter ultraviolet and X-ray sightlines through our neighborhood, so the local bubble is a local quiet zone shaped by past explosions. The sky has a faint afterglow from the universe's infancy, the CMB. This relic light shows tiny temperature ripples at microkelvin amplitude. It matters because those fluctuations define the quietest cosmological signal we can observe. Shortly after recombination, photons streamed freely, and diffusion smoothed smaller irregularities. Pressure waves left large-scale peaks, while damping erased small-scale noise. Satellites like WMAP and Planck measured variations down to tens of microkelvin across the whole sky. Those maps show the early universe was remarkably calm, on average, with only tiny density contrasts. So the CMB sets an absolute quiet benchmark for cosmic structure formation. The moon's far side faces away from Earth, creating radio silence. That far side is shielded from human-made radio chatter and many earthly emissions. Astronomers prize it because removing local interference boosts sensitivity hugely. The moon acts like a physical radio shield, blocking broadcasts and ionospheric noise. Proposals for low-frequency arrays their aim to detect signals from the universe's first stars. Engineers design careful shielding and remote deployment to minimize systematics and self-noise. Studies estimate orders of magnitude quieter conditions in important bands compared to Earth's ground telescopes. So the lunar far side becomes a near-perfect laboratory for faint cosmological radio searches. Some nebulae cool to astonishingly low temperatures, becoming thermal deserts. These regions matter because lower temperatures mean far less infrared emission. Rapid expansion or radiative inefficiency carries heat away, letting gas cool to near 1 Kelvin. Dust and molecules radiate weakly when sparse, which suppresses thermal brightness. The Boomerang Nebula measures about 1 Kelvin, colder than the cosmic background. Observers find unusually low infrared brightness and very faint emission lines there. Those conditions create quiet windows for sensitive detectors looking elsewhere. So certain aftermath regions act like cold, quiet pockets in the galaxy. Dense molecular clouds appear as dark silhouettes against starry backgrounds. Their interiors are cold, dense knots where chemistry quiets down. These cores matter because planet formation begins in their shielded interiors. Dense gas and dust block external starlight and reduce ionization from cosmic rays. Shielding lets temperatures drop and molecules freeze onto dust grains, lowering emission strength. Prestellar core L1544 shows densities thousands times the ambient interstellar medium. Observers measure very narrow spectral lines there, indicating minimal turbulence and motion. That calm environment helps complex molecules survive and seeds future planetary systems quietly. So molecular cores act as secluded, chemically quiet cradles for worlds. Far beyond Neptune, the solar wind thins and the heliosphere fades. The heliopause marks where solar influence ends and interstellar space begins. This boundary matters because noise characteristics change abruptly there. Solar particles slow, magnetic fields reconfigure, and particle densities fall further. Plasma waves weaken without strong nearby sources, and local emissions drop. Voyager 1 recorded changes in plasma density and a calmer magnetic environment beyond. Those measurements helped scientists separate local effects from true galactic backgrounds. So the heliopause represents a transition to more pristine and quieter space. We visited voids, the local bubble, the CMB, and lunar radio havens. Remember the opening claim: silence comes from vanishing particles and weak emissions. If you liked this quiet tour, subscribe for more curious science explained plainly. Thanks for listening. Space is quieter than most people expect.